So let's summarize this, because really what we had in this case, in these three examples, is we had three different types of asymptotes for horizontal asymptotes. We're not going to worry about the vertical asymptotes right now. For the first one, we had a horizontal asymptote at 0, right? This function approached basically 0. In the second case, we had that the function approached a value of 1/3, or something other than 0. And in the third case, we had a function that approached this slant or oblique asymptote. And the key to identifying which one is going to happen is by looking at the degrees of the numerator and the denominator. So the idea is, if the numerator has a lower degree than the denominator, like in the first case, basically that denominator is going to dominate. The denominator is always going to be bigger than that numerator, because when you plug in very large values, the bottom is going to get very big. So just to take a quick note here, we have this summary table. So the horizontal asymptote equals 0 when the degree of the numerator, so notice here we're dealing with function p over q, right? So when the degree of p is less than q, right? If p is our numerator and q is our denominator. So that happens when, basically what happens is if we have a function like x over x squared plus 5, I just made this up, basically what's going to happen is the denominator, when x is very, very large, the denominator is always going to be very, very, very big, right? So what that's going to happen when the denominator is big is the function's going to essentially go to 0, right? So our horizontal asymptote will be at x equals 0. So our horizontal asymptote, HA, is going to be at x equals 0. Oh, no, not x, y equals 0, right? Because it's going to be a horizontal line, y equals 0. There we go. So the second case we had was when the degree of the numerator and the degree of the denominator were the same value. So in this case, we had a linear over a linear, but it could be a quadratic over a quadratic or a cubic over a cubic. And what means that in this case is that the numerator and the denominator both matter in determining where that asymptote is, because they're sort of equally as powerful. So the degree of p is equal to q, right? So for example, x squared plus 5 over 3x squared plus 3x minus 2, right? In this case, we would get a horizontal asymptote as well. But what's going to happen is this function up here and this function up here are sort of going to fight and pull that horizontal asymptote away from 0. And we'll talk about how we get it to do that in a minute. But basically, the horizontal asymptote is going to be at y does not equal 0. So it's going to be something other than 0, but it is still going to be a horizontal asymptote. And the last case, we get an oblique or slant asymptote whenever the degree of the top is larger than the degree of the bottom. So in this case, we had a degree 2 over a degree 1. And what this does, so let me write that down first. So degree of, degree of, in this case, P is going to be greater than Q, right? When the top has a larger degree than the bottom. So what it's basically doing is that horizontal asymptote that we saw when the degrees were even are getting pulled and stretched and rotated sort of by that top function being more powerful. So that top function sort of pulls that horizontal asymptote to be on an angle. And that's essentially what happens. So an example of this would be x squared plus 3x plus 5 over x minus 2, right? We have a degree 2 over a degree 1. In this case, we have a slant asymptote. Okay? So now the question becomes, let's find the equations of those lines. So we already know how to find the equation if the horizontal asymptote is at 0, because if the degree of the denominator is always bigger, we know we're just going to have a horizontal asymptote at 0. But for the other two, how can we actually find the equation of these asymptotes? That's where we're going to go to the next page to answer some questions, and then we'll come back and finish this table. Okay, so here we go. We have a function here, x squared minus 1 over x cubed. So first thing we can do is usually we like to factor and see if something's going to cancel out. But we can tell right here that nothing's going to cancel out. Let's just factor though, just for the sake of it. So we have x minus 1, x plus 1 over x cubed, right? That's what our function is going to equal. As you see, nothing's going to cancel, right? So we can first find our vertical asymptotes, or holes, if this function has any. And that occurs where the denominator equals 0. So does that happen? Well, yeah, the denominator can't, to make the denominator 0, all we need to do is plug in x is 0. So x cannot equal 0. So therefore, we have a vertical asymptote at x equals 0. That's pretty straightforward for our discontinuities, right? We know it's a vertical asymptote because it doesn't cancel out, right? That would make a hole. So that's vertical asymptotes, that's easy. Let's now determine the end behavior of this function. So thinking about what we just did, remember, we have a function and the degree of the top, what's the degree of the top and the degree of the bottom? So the degree of the top is 2. So we basically have a degree 2 function over a degree 3 function, right? In terms of our values there. This tells us that the bottom is going to dominate. So this number is going to get very large. As x goes to infinity, basically this function, the bottom part is going to get very, very, very large. So the y value is going to approach 0, right? Does the same thing happen for negative infinity? Well, it does. If you were to plug in a very, very large negative number at the bottom here, basically you're going to have a smaller number on top divided by a larger number on the bottom. So also, as x goes to negative infinity, y goes to 0, because that bottom is going to dominate. So essentially what we're saying is we have a horizontal asymptote at y equals 0, right? Again, this will happen whenever the degree of the bottom is bigger than the degree of the top. So there we have our vertical asymptote and our horizontal asymptote. Next question. We don't have to sketch it. Actually, in the next lessons, we're going to learn how to sketch it. But for now, let's just worry about finding these things. So let's take a look at this one. Ooh, this looks like fun. We have two quadratics, quadratic in the top and the bottom. So first, let's start off by finding any discontinuities, right? And we can do that by factoring. I'm actually just going to do the factoring off to the side just to not make everything super messy. So for the top, we have 4x squared minus 4x minus 1. Can we factor that? Two numbers that multiply to -4 and add to get -4. So we know. Are there any numbers that do that? And the answer is no, I don't think so, right? So this is going to be not factorable. Okay, so let's worry about the denominator now. 9x squared plus 12x plus 4. First of all, can we factor anything out? No greatest common factor. So two numbers that multiply to give us 36 and add to give us 12. And those numbers are just going to be 6 and 6, right? 9x squared plus 6x plus 6x plus 4. I was surprised I could do that fast. And then we factor by grouping 3x plus 2 plus 2, 3x plus 2, there we go. So it does work. Let me just put equal signs here, make it nice and neat. So our factor form would be 3x plus 2, 3x plus 2. Oh, it's a perfect square trinomial. I should have identified that right off the bat, 3x plus 2 squared. So we can rewrite this function as 4x squared minus 4x minus 1 over 3x plus 2 squared, right? So the question is, where are the vertical asymptotes going to be? Where are the discontinuities going to be? So that always comes from the denominator. What makes this equal to 0? Well, 3x plus 2 cannot equal 0. So in this case, x cannot equal -2/3, right? So therefore, we have a vertical asymptote at x equals -2/3. That's pretty straightforward. We know it's a vertical asymptote again because nothing cancels out. So that's good for that. can we now find the end behavior, or the horizontal asymptote, if it has one? Well, let's think about it. The top and the bottom both have degree 2. So we have degree 2 over degree 2. And this is where it gets a little bit different, because the top and the bottom are basically going to fight over where that asymptote goes, that horizontal asymptote goes. So the trick to do this is actually to factor the highest power out of the numerator and the highest power out of the denominator. It's just a little trick. You'll see why it works in a second. So essentially what we're going to do is we're going to take the numerator and we're going to take out the highest power. And the highest power of the numerator is going to be x squared, right? That's the highest thing in the top. So let's factor out an x squared out of the top. If we do that, we're going to be left with a 4. And then essentially what it's going to be, it's like when you take a highest power out of something, or when you factor something out, you're essentially dividing it, right? So it's like saying 4x over x squared minus 1 over x squared, right? That's how you would factor that numerator if we factored out the highest term. You're just dividing each term by x squared, essentially. And the same thing in the denominator, x squared, and then what's left is 9 minus 12x over x squared plus 4 over x squared. So notice a few things happen here. First of all, we can cancel out those x squareds, right? That's the first step. And we can also notice what happens to all these other terms, right? We have a constant term 4 in the top, and we have these two terms here. We have a constant term 9 here, and these terms here. But remember, when we're looking for the horizontal asymptote, we're really looking for the end conditions. So what we want to know is when x approaches infinity, what happens to this thing? Well, think about it like this. When x approaches infinity, this 4, is that 4 going to change? No. If we plugged in a number, though, very close to infinity, like a really, really large number, to this term, what was going to happen? Well, it's like, say we plugged in 1,000,000. It's going to be 1,000,000, or 4,000,000, over 1,000,000 squared. And 1,000,000 squared is a lot of zeros, right? So basically this term is going to get very, very close to 0, right? So we can show that like this. I'm just going to rewrite this out. 4x over x squared minus 1 over x squared. This is all over 9 minus 12x over x squared plus 4 over x squared. So what's going to happen is this term is going to go to 0 when x goes to infinity, because the bottom, the numerator, or the denominator, that x squared, is going to dominate that, right? It's going to make a very, very large number. Same thing's going to happen here, because when x gets very large, 1 over a very large number is going to be basically 0. In the denominator, the same thing happens, right? That 12x over x squared, the x squared is going to dominate when we get very large. So this thing is basically going to go away. And also, the last term, this thing is going to go away. So essentially what we get is 4 over 9. That's all that's left when those other terms go away. And in fact, if we were to graph this, we would see that, that the horizontal asymptote occurs at 4 over 9. Now the thing to ask ourselves is this true also when x approaches negative infinity, right? If I plugged it, so this is true when x approaches infinity, but if we plugged in a very, very large negative number, would it be the same thing? And the answer is yes, because you still have a very large number in the bottom, and that's still going to make this thing go to 0, and that's true for all of them. So that also applies when x goes to negative infinity, right? So when x goes to infinity and when x goes to negative infinity, I'm just going to write it over here, y goes to 4 over 9. Oops, I should do it like this. Y goes to 4 over 9, and y goes to 4 over 9 for both positive and negative infinity. So again, that little trick that works basically when the numerator and the denominator are the same degree to find where that horizontal asymptote is to factor out the highest power out of the numerator and the denominator, and then think about what happens when x goes to infinity and negative infinity. A lot of things will disappear, and what you're left with is where that asymptote is. So I actually just wrote out that final answer for this question a little bit nicer. As x goes to infinity, y goes to 4 over 9. As x goes to negative infinity, y goes to 4 over 9. So therefore, we have a horizontal asymptote at y equals 4 over 9. That makes it clear what the final answer actually is for this question. So let's now summarize this in the table up here, right? So far what we have. So we can find, when the horizontal asymptote is at 0, that's when the degree of p, or the degree of the numerator, is less than the degree of the denominator. So we find the equation of that horizontal asymptote because it's just always going to be y equals 0. That one we don't really need to find. But when we want to find the horizontal asymptote when the degrees are the same, we factor out the highest power and check what happens when x goes to infinity and negative infinity and negative infinity. Okay, just like we did in that previous question. Also down here, we can look at what the end behavior is for these. So the end behavior for a horizontal asymptote at 0 is just going to be as x goes to infinity, y goes to 0, and as x goes to infinity, y goes to, or negative infinity, sorry, y goes to 0 as well. And then for the horizontal asymptote not at 0, it's going to be the same thing, but it's going to be some other value other than 0, right? So as x goes to infinity, y goes to some value, I'm just going to call that value L. And as x goes to negative infinity, y will usually approach that same value L. Okay? Now the question is, what happens with an oblique asymptote or a slant asymptote? How do we find the equation of that slant? And it's actually not as complicated as you think. We have this fancy trick called dividing for polynomials, right, that we learned in the last unit. And the actual cool thing is that when you divide the numerator by the denominator, so when you do p of x over q of x, the quotient, the answer you get out of the division statement, is just the equation of the asymptote. So you're going to do the division, or you're going to divide p and q. The quotient is the equation of the asymptote. If you're T-O-T-E, if you're interested in why this works, there's lots of resources online you can check out, or you can come talk to me about it. It's sort of interesting why this ends up working. But anyways, the quotient is the equation of the asymptote. So the thing to keep in mind is that this is sort of like a polynomial function where the function is either going to approach infinity or negative infinity as x goes to infinity. So for the end conditions, as x goes to infinity, y is either going to go to plus or minus infinity. I'm going to put a question mark there to indicate it's going to go to one or the other. And as x goes to negative infinity, y is also going to go to positive or negative infinity. It's usually the opposite one as the x going to infinity. So let's see how this actually looks in a question. So going to example C here. First of all, let's find any discontinuities. So the denominator can be rewritten as, well, 3x minus 1, x minus 2, x plus 1. It's already factored for us here in the numerator, so don't need to worry about that. The denominator can be factored as, it's a perfect square, right? So it's going to be x plus 2 squared. Does anything cancel? Nope, doesn't really. Sort of boring, right? Nothing ends up canceling here. So that tells us that we're going to have what kind of discontinuity? Well, this tells us here that x cannot equal negative 2. Cannot equal negative 2. So therefore, we have a vertical asymptote at x equals negative 2. It's not a whole because it appears in our final equation, right? And that's our only discontinuity. Now looking at the end conditions of the function. So we notice that the top is factored, but it is a cubic function. So in order to divide it, we actually need to unfactor that. So just doing a little bit of distribution here tells us that our would actually be, I'll just do this part for you. So our function is actually 3x cubed minus 4x squared minus 5x plus 2, and that's all over x squared plus 4x plus 4. So we notice that the top has degree 3 and the bottom has degree 2, right? So when the degree of the top is bigger than the degree of the bottom, we need to check out, it might be a slant asymptote, right? So we basically need to find that. And the way we find it, just as we discussed, is by dividing those two things. The quotient is going to be the equation of that asymptote. So I'm going to let you divide, and then we'll come back to the question and discuss. So after doing the division, this is what I got. The quotient ends up being 3x minus 16. Notice how we have a remainder here as well, but we don't actually care about that. The slant asymptote is going to have the equation of the quotient, which is 3x minus 16. So what is this actually going to look like? Well, 3x minus 16 is just a line, right? And the line is going to look something like that. It's going to have a negative y-intercept and it's going to be a positive slope, right? So that tells us what the end conditions of the functions are going to be, right? Because as the function goes to infinity, it's going to approach this line, either from the top or the bottom, something like that. And as x goes to negative infinity, the function is going to approach like that, right? So this tells us as x goes to infinity, y also goes to infinity. And as x goes to negative infinity, y goes to negative infinity. And we also know that the slant asymptote, therefore we have a slant or oblique asymptote, at an equation of y equals 3x minus 16. There we go. So just with a little bit of division, we can find out what our end behavior of that function is going to be. Now I want you to try this last question yourself. After you try it, unpause the video and we'll go over the answer quickly. So here is the answer to that problem. We know we have a vertical asymptote at x equals 2 because the denominator cannot equal 2. It's not a whole because nothing canceled out. We also know we can divide the 2 because the top has a degree of, the numerator has a degree of 2, right? And the bottom has a degree of 1. So that means we could possibly have a slant asymptote, and we find the equation of it by dividing. I divided using synthetic, and what I got is that the quotient is x minus 2. I quickly then graphed it to see that it's a positive slope, which tells us what the end behavior of the function is. As x goes to infinity, y goes to infinity, x goes to negative infinity, y goes to negative infinity, and the slant asymptote has an equation of y equals x minus 2. There we go.